Hello, this is Wenchel Land from the Naval Postgraduate School's Space Systems Academic Group. My co-authors are Lieutenant Harrison English and Dr. Jim Newman, also in the Space Systems Academic Group, and Dr. Fabio Alves with the Physics Department. Our talk today is about how we think terahertz imaging can be achieved with small satellites at a relatively low cost. The first question that may come to mind is, why terahertz? Because terahertz is on the lower end of the infrared frequency band, it can image colder objects better than IR and long-wave IR sensors, as long as the object is illuminated by the sun, which is an ideal terahertz source. If we look at Planck's radiation curves, shown over here on the right, the peak radiances at temperatures lower than 150 Kelvin, or approximately negative 120 degrees Celsius, occur below 10 terahertz. Another advantage of this frequency band is that it can penetrate non-metallic solids and some liquids and gases, which opens up the possibilities of missions that could use this technology. Terrestrial terahertz imaging applications exist, most notably in non-destructive evaluation in the aerospace industry. But because terahertz energy is mostly absorbed by water vapor, the imaging capability, in theory, will be much better from space. We are hoping to explore this possibility with a simple, small, low-cost solution that may enhance mission sets such as space domain awareness and rendezvous and proximity operations. The payload we're developing leverages MEMS technology that can be tuned to absorb the incoming terahertz energy on one side of the focal plane array using a metallic thin film and emit energy in a targeted IR band. For example, the uncooled microbolometer COTS cameras that we're working with are sensitive between 8 and 14 micrometers. This concept is shown here for 1 pixel of the terahertz to IR converter. When we combine the terahertz to IR converter with the COTS camera, this results in a low-cost, small form factor terahertz imager. The payload computing stack consists of a Raspberry Pi 3A+, a Pi capture board, and a custom RS-232 converter board. There are 2 cameras in this payload, one to capture reference images in the IR band, which is well understood, and the other in the terahertz band. The COTS hardware, which has been modified for spaceflight, has been qualified to Geb's vibration levels, and we've performed confidence testing in thermal vacuum from negative 40 to 80 degrees C. Further testing is pending flight-specific requirements. We used a plug-and-play approach to maximize flight opportunities for the TIC payload. The host application Link1, or HAL1, is middleware that we developed at MPS. It is easily compatible with multiple spacecraft buses, although the buses must be known beforehand. Not only does it detect and configure itself to a spacecraft bus, it also contains the command structure for the payload, which facilitates integration with the bus. The data flow from the payload through the bus to the ground station is shown here. The TIC payload has been successfully tested on the bench, and the pictures shown here were captured using HAL1 and both of the IR and terahertz cameras on the left and right over here. No issues were encountered during normal operations, and several failure modes were also tested, and the errors were logged by the payload. The picture on the bottom is of a really hot soldering iron tip that shows it is possible to capture terahertz energy with the TIC. However, no post-processing was performed on any of these images, but we would expect tremendous enhancement with common processing algorithms. Using Astro Digital's 6U bus and the MC3 network as a baseline, we developed a preliminary concept of operations that is representative of what a tech demo mission might include. Notionally, we assumed that the solar panels are placed in the sun tracking direction, the radios are placed on the nadir pointing face, and the cameras are facing out the orthogonal direction. For the preliminary CONOP, we modeled a 500-kilometer sun-synchronous orbit in STK and selected several targets, including an MC3 ground station, 2 ground targets, and 2 space targets. In this scenario, the spacecraft flies over the MC3 ground station at MPS first. The spacecraft defaults to the sun tracking mode, so you'll see it return to that mode between targets. The next target we considered is a co-orbiting spacecraft, which we hope will provide some insight into how terahertz imaging can be used for proximity operations. This animation is at 10 times real-time speed, so we are expecting that the spacecraft would stay in view longer than just a few seconds. We're also interested in imaging ground targets that have varying levels of humidity within Earth's atmosphere, which may help us better understand the TIC payload capabilities. Ranajantila, India, has a 51% average relative humidity, which is a representative high humidity ground target. The second space target coming up, for a brief moment, is the second brightest star in the Orion constellation, also known affectionately as Betelgeuse. We chose this one to test if the terahertz imaging is possible for imaging distant objects. I'd like to take a moment to point out that the Astrodigital bus uses the Max Flight software, which also runs the SDK Solus plugin, and that allowed us to run these simulations in SDK with engineering development units of both the CNDH and the TIC payload in the loop. Being able to develop the ConOp in SDK and then test the software with both real hardware and simulated bus parameters was very valuable during the design process. The final target in the simulation, which is a representative low humidity target, is the McMurdo Dry Valleys in Antarctica. In contrast to Ranajantila, it is one of the coldest places on Earth and has had no rain in millions of years. These locations were chosen based on the orbital parameters selected for the simulation, but again, they are representative imaging targets for the initial set of data to be collected for the tech demo, and highlights possibilities for space-based terahertz imaging. The Terahertz imaging payload is ready for flight-specific integration and testing, and we're working towards a 2022 launch opportunity. If there are any questions, please don't hesitate to contact us. Thanks for watching.